A few lessons ago, we were solving right triangles, meaning if you were given some information about the sides and angles, could you solve for the missing sides and angles? But it only worked for right triangles. In this lesson, I'd like to use something called the law of sines that you can use to solve any triangle, not necessarily a right triangle. Just to be consistent for this lesson, for my triangles, I'll make them look all kind of the same. I'll write the angles as A, B, and C going in this direction, and then the sides opposite the angles are just lowercase letters. So what does the law of sines say? The law of sines states that if you take sine of an angle and divide it by its opposing side length, that's equal to the same thing for the remaining sides and angles. That is, it's equal to sine of B over B and sine of C over C. If you take those three values and divide them, they're always going to be equal in any triangle, not just a right triangle. We can use this law to solve any triangle that we'd like. I think I'll note here that if you flip all of these fractions, these three things will still be equal to each other. So you can also state the law of sines as A over sine of A is equal to B over sine of B, which is equal to C over sine of C. So this is an equivalent formula for the law of sines. Here in example 1, I'd like to solve this triangle. So here we have that A has an angle measurement of 47 degrees, C has an angle measurement of 76 degrees, and the length of side A is 8. So what we're looking to do is solve for angle B and side B and C. I think to start with, the easiest thing to solve for would be angle B, if you want to know this thing here. The reason that we can solve this is if you take the three angles that appear within the triangle and add them together, that is equal to 180 degrees. And we already know two of them, so we can solve for the remaining one. So that is the measure of angle B is equal to 180 degrees minus 47 degrees and minus 76 degrees. Easy enough to compute this in a calculator, so I'm just going to type this stuff in. And here we go. The measure of angle B is 57 degrees. And we haven't used the law of sines yet, but we're already on our way. So that's 57 degrees. Now, how can I solve for either B or C? If you're going to use the law of sines, here's one way to do it. Since you want to solve for B, B has to appear in your formula. In the law of sines, I'm going to write, well, sine of angle A divided by side A is equal to sine of angle B divided by B. The only thing that I don't know from the law of sines is B. I can plug in all the other necessary information and solve for the remaining piece. Now, the second thing to point out is, perhaps since we're solving for B and in this formula it's in the denominator, maybe I'll use the other variation of the law of sines. That is, A over sine of A is equal to B over sine of B. So I'm going to take all of the information from here and put it into this formula. The only thing that I won't know is B. So let's see, A is equal to 8. Sine of A is sine of 47 degrees. That's equal to B, the thing I don't know, divided by sine of 57 degrees, the thing we actually just solved for. If you want to solve for B, I can multiply sine of 57 degrees to this side of the equation. So what we get is the following. 8 times sine of 57 degrees divided by sine of 47 degrees is B. The next thing to do here is just go to your calculator and enter in all of this information. I'm going to do that, and I think what I'll do is round B to the nearest tenth. So let's see, making sure my calculator is in degree mode. That's 8 times sine of 57 divided by sine of 47. Okay, it's a decimal that goes on a little bit, but if I round to the nearest tenth, I get 9.2. Approximately. That's pretty good. All right, so I now know something else about my triangle. I know that B has a length of 9.2. The only thing that I don't know is C. Now here you can't use the Pythagorean theorem because we don't have a right triangle. None of the angles are 90 degrees. All that means is we can use the law of sines one more time. This time I'm going to choose to use a formula that has a C in it. So I have to use like sine of C and C. Second of all, I'm going to put the C in the numerator just to make it a little bit easier to solve for C. So I guess I'll use the following. I'll say, let's see, C over sine of C is equal to A over sine of A. You only have to use two of the different parts, but in this formula, I know angle C, side A, and angle A, and the only thing I don't know is C. Let's plug everything in and see what we get. We have, so I don't know C, this is sine of 76 degrees. That's equal to A, which is 8, and that's divided by sine of 47 degrees. To solve for C, I can multiply sine of 76 to this side of the equation. So let's see, C is equal to 8 times sine of 76 degrees, all divided by sine of 47 degrees. Again, I'm just going to my calculator and I'm typing this in and see what we get. So that's 8 sine of 76 divided by sine 47. And if I round to the nearest tenth, I get 10.6 is the length of side C. So I'll put that up here. We have solved this triangle. It's not a right triangle, but what I know is the measure of every angle and the length of every side. I think one other thing to point out here is there are names given to the cases that you're working on when it comes to solving a triangle. Like here, we're given an angle, and a side. This is often abbreviated angle, side. So here is a particular case that you can always use the law of sines to solve. Let's use the law of sines to solve this triangle and see if it's possible. As I mentioned in the previous example, I think we can refer to this case by the information given. Like here we're given an angle, a side, and an angle. And the setup was different than in example 1. Like here, the side this time is actually between the two angles. So the way that this information is actually given in the triangle is as follows. You're given an angle, a side, and an angle. You can use the law of sines to solve this particular case. So it's slightly different than the previous example only because the side is between the two angles as opposed to adjacent to only one of the angles. Okay, well, all that being said, how do I solve for the missing parts? First of all, angle C, maybe we could find that, but I also want side A and side B. I still think starting with finding the measure of angle C is probably a good place to begin. Again, the reason for that is if you add the three angles together, that's going to be equal to 180 degrees. Therefore, if you want to know the measure of angle C, you can take 180 degrees, subtract off the measure of angle A, which is 42 degrees, but also subtract off the measure of angle B, which is 48 degrees. So I'm just, typing this in, don't want to make a mistake here. And C is actually a 90-degree angle. It turns out for this problem that, well, we actually do have a right triangle. So I could go back here and say, well, this angle I drew in here, I probably could use this other notation for it and say, oh, well, we actually have a right angle. So you're not actually allowed to use the Pythagorean theorem if you want to solve for parts of this triangle, but I still want to stick with the law of sines just to go over what that would look like for this problem. So we did solve for the measure of angle C. It's 90 degrees. This is technically a right triangle, but the law of sines still applies. Okay, so we have one thing solved for. Let's solve for, I think we could do either, but maybe I'll solve for A first. So I think what I'll use is, so angle A and side A, And maybe I'll use, well, I guess I have to use angle C and side C. I'm stuck using those two things. So the way I'm going to set up the formula is as follows. A is the thing we're solving for, and I'm dividing by sine of A. This is equal to C, which is something I know, over sine of C. Okay, this thing. If I plug in all of the information I know, we have A divided by sine of 42 degrees. This is equal to C, which is 12. That's divided by sine of 90 degrees. Okay, if you're looking to solve for A, just like last time, you can multiply sine of 42 degrees to this side, and that gives us A is equal to 12 times sine of 42 degrees all over sine of 90 degrees. And this is something you can plug into your calculator and then round your answer, again, let's say to maybe the nearest tenth. By the way, sine of 90 degrees is an exact value that we know. It's equal to 1. You can still type that into the calculator. It's still going to work if you want. But since this is equal to 1, you really only need to enter in this stuff from the numerator. So that is 12 times sine of 42 degrees. The value I get for A, if I round to the nearest tenth, is 8.0. So the reason the law of sine still works for a right triangle is because, well, sine of 90 is a value that we know exactly, but it works exactly the same way. Okay, so I know A is equal to 8. I don't know B. So to solve for B, now here we have some options. I'm going to say, well, I'll use B over sine of B is equal to, maybe I'll use A over sine of A. B is the only thing I don't know. Sine of B is sine of 48 degrees. A is equal to 8, and that's sine of 42 degrees, like this. To solve for B, I can multiply sine of 48 degrees to the other side of this equation. So I have 8 times sine of 48 degrees all over sine of 42 degrees. Now here I have to enter all this into the calculator. So 8 sine of 48 divided by sine of 42. And if I round to the nearest tenth, I get that B is equal to 8.9, approximately. Okay, so I look back at the triangle. I've found the only angle that was missing, which is C, and then the two other sides, so we have solved this particular case. All right, now I'd like to talk about something called the ambiguous case. If you're given a side, and then an angle that's not between the two sides, you could potentially have either no triangle, one triangle, or two triangles. And that's the reason for this name, the ambiguous case. Based on the information you're given, it's possible that you can't even construct a triangle. Or maybe you can construct only one. Or very strange, maybe you could actually construct two. Let's actually explain this. But for starters, I want to keep the way I draw the triangles the same. So the triangles that we've been drawing, so I'll just draw a real basic one over here. I'll always put angle A here, angle B here, and angle C here. And then the sides are opposite the angles like this. So I'm going to make up some numbers and try to construct a triangle just to see what it would look like. So let's say, A was equal to 1. We'll say B is equal to 10. And then the measure of angle A is, maybe we'll say something like 50 degrees. So here, I'm giving us information about this side, and this angle. And I'll try to draw it more accurately down here. Oh, because I'm given angle A, and I'm not told anything about the length of side C, I'm going to start by just, putting an angle in here just to work with, but I won't extend the length of this side. So in trying to draw this triangle, I'm going to start by drawing, maybe that's like a 50-degree angle. So here's angle A. It's 50 degrees. I can't extend this side out any further because I'm not given what C is equal to, but I am told that the length of side B is 10, so I'm just going to draw something that is this is like a length of 10. So here's B. I'm told nothing about angle C up here, but I am told that the length of side A is equal to 1. Just from the numbers I've picked, I don't think this is going to give us a triangle, and here's why. If the length of B is 10, so let me draw this in here. This is 10, and this angle is 50 degrees. If you go a distance of 1 from this point, which that's the side A, there is no way you're ever going to get down to this side to actually construct a triangle. So let me just extend a dotted line here. Like this is the length of side C, or this is where side C has to be. If A is only 1, it doesn't matter what angle you draw up here. You're never going to reach this side to construct a triangle. It's impossible. So like the best you can do is draw something that looks like, like this. But that's no good. Like you'll never actually make it down here. I'm going to go over a quick formula that you can use to determine this type of case. Like when does it turn out that you never get a triangle? What you can do is draw in this distance here at a right angle, and I'll call this H. For you to construct a triangle, A has to be at least as long as this line or longer to actually get a triangle. So how big is H? Here we can use some right triangle trigonometry. I'm going to use the following. I'm going to use sine. Sine is opposite over the hypotenuse, which we do have in this right triangle. So all that being said, sine of A is equal to the opposite, which I'm calling H, over the length of B, which is 10. So here, if I solve for H is equal to 10 times sine of 50 degrees. I'm going to get a number for this in my calculator. 10 times sine of 50 degrees. And I get about 7.7. A has to be this length or longer. If it isn't, there is no way you can construct a triangle. So like here's a nice thing to look at as a guide. If you want to know if you have a triangle or not, you could think about, well, what is this distance here? If A is shorter than H, so that is, if A is less than H, there is no triangle. So I'll just jot that down again. No triangle in this type of situation. Now, why is it possible that you could get two triangles? So let's draw this picture again. So, you're drawing, okay, you got your 50-degree angle, and the length of this side is 10. And the only other thing that you know is the length of side A. How is it that you could actually end up with two triangles? So, here's that vertical distance again. The way you could get two triangles is if A is long enough that it's longer than H, but it goes over here like this. So here's one value of A. But potentially, your second triangle can come in over here like this. So what happens here is if A is longer than H, but it's shorter than B, you could draw that distance over here to get this one triangle, or you could draw A over here to get this second triangle. So it's a very strange thing. Like, for certain values of A, you can actually end up with two triangles. So, that is, if A is greater than H, but is less than B, there are actually two triangles. So I'll mark that here. And if A was actually longer than B, that means you could only draw your other side in over here, and there would be only one triangle, and that is the final case. If A is greater than B, there's exactly one triangle. Now this is fairly abstract, and I think it would be helpful to look at this in a couple of examples. So here in example 3, explain why there is no triangle that can be formed by a side length of A equaling 20, B equaling 26, and an angle A of 80 degrees. So I'm going to do my best to try to draw a picture for this. So let's see. I'm going to start by, I like drawing the angle first. So here's angle A. It's pretty steep, 80 degrees. And I'm told B is equal to 26. And that just means for my drawing, I'm going to go out some distance that I'm saying is 26. And now A is equal to 20. So that's this side here. It's a distance of 20. If that number, 20, is not longer than this distance h, so that is, if A is shorter than this length h, there's no way it can reach side C to actually get our triangle. So I'm actually going to figure out, well, what is this value of h? This is a right triangle, and I know that sine of angle A is equal to h over b. And I have numbers for everything except h. So that is, I can multiply both sides by b, and I'll plug 26 in for b and 80 degrees in for a, and that's going to be equal to h. I'll put that in my calculator. So that's 26 times sine of 80 degrees. And I get 25.6 if I round to 1 decimal place. So here's h. And here's the problem. If you draw in A is only 20. And that means there's no way it can reach side C, no matter what angle we approach this top from. It'll never go lower than this distance here. So said another way, because A is less than h, there is no triangle. There is nothing left to do. There's nothing to solve for. Okay, here in example 4, it says find both triangles that can be formed by this information. So let's see, I have a side to side and an angle. So I know this is the ambiguous case. And of course, this angle is not between those two sides. All right, I'm going to try to draw a picture for this one. Okay, an angle of 56 degrees. If I draw that over here. So here's angle A, a little steeper than a 45-degree angle. Okay, this side here is B, which is 18. Okay. And then A is 16. Okay, one thing to point out here is A is less than B. And this means with the ambiguous case, there's only two possibilities, that there are no triangles or there's two. Okay, let's see what that falls in, which of those two categories. I'm going to figure out the distance h here. So I'm going to extend side C and think about what this distance h is. So again, we have that sine of A is equal to h over b. If I multiply b to the other side, I get b times sine of A is equal to h. I'll plug 18 in for b and 56 in for A. Go to my calculator. 18 times sine of 56 is 14.9. What does this tell me? Okay, this falls into the category of two triangles because A is greater than h, but it's less than b. So there's two possible triangles that you can draw in here. Okay, one, if you draw A is equal to 16, since it's longer than h, it can make it down here. That gives us this triangle. So we have this possible triangle. But also, so here this was A, this is one of our possibilities, but also A could be drawn over here, like this, giving us this second triangle, which I'll draw in black over here. These are the two triangles that you can get. So here this is A, which is 56 degrees, B is 18, and A is equal to 16. I don't know the measure of angle B, and I don't know the measure of angle C, and I don't know the length of side C. Likewise, in our second triangle, again, A, it still is 56 degrees, B is still 18, A, that's still 16, and I still have a triangle, but I don't know B, I don't know C, and I don't know the length of side C. What we'll do is solve these two triangles separately, and I'm going to start with this one first. So here's the information that we had on the triangle, and we do not know measure of angle B or C or side C. All right, I guess to start with here, well, we only know one angle, so I can't start by solving for one of the other two. I think what we can do is solve for the measure of angle B first. And I'm going to use the law of sines to do this. I know that sine of B over B is equal to sine of A over A. I'm choosing to write the angles in the numerator because, well, the angle is the thing I'm solving for. And in this formula, the only thing I don't know is B. I have numbers for everything else. So this means sine of B over, okay, B is 18. That's equal to sine of A, which is 56, all over 16. I can solve for sine of B at least by multiplying 18 to the other side of my equation. So sine of B is equal to 18 times sine of 56 all over 16. Okay, I'm going to type this into my calculator and see what we get. So that was 18 times sine of 56 divided by 16. Okay, I get that sine of B is equal to 0.93266722691. Now, that's not B, that's sine of B. But there's a really nice way to get sine, or actually, I'm sorry, B, all by itself. I can apply sine inverse to both sides of my equation. Sine inverse of sine cancel to give me B. And here on the right side, I have a button in my calculator for sine inverse. So I'm just going to take that value, 0.93266722691, and then just type that into my calculator to see what value I get back. Okay, sine inverse of that number, 93266722691. I guess I'll round maybe to one decimal place, but this is 68.9 degrees. And that looks pretty good for this angle. Put this up here, this is 68.9 degrees. Yeah, you know, it's definitely less than 90 degrees. I mean, this seems to be good with my picture, so we got it. We got angle B. Oh, this means we can get angle C pretty easily. The sum of angles A, B, and C equal 180 degrees. The only thing I don't know is C, which means I can take 180 degrees, subtract off A, and subtract off B. And the measure of angle C, which just get this again from my calculator, is 55.1. You might have to round only to the nearest, I guess, whole number, but you know, this is fine too for this problem. The only thing that I don't know is what is the length of side C. And I think we can use the law of sines to get this. So what I'm going to do is, I guess I'll do C over sine of C is equal to A over sine of A. Again, putting the C in the numerator because that's the thing I want to solve for. So C I don't know. Sine of C is sine of 55.1. A is equal to 16, and sine of A, that's sine of 56. I will multiply this to the other side of my equation, leaving me with C. C is equal to 16 times sine of 55.1 degrees, all divided by sine of 56 degrees. Go to my calculator. Sine of 56. Okay, C is equal to 15.8 if I round to the nearest tenth. But that's it. I know everything about this triangle in terms of the angles and sides. Now, why is there a second triangle? I'm going to draw its picture, and we're going to go through a very similar process to try to solve it. So here's the other possible triangle that we could have, and we still don't know angle B or C or side C. Well, I guess like last time, what we can do is still, start by solving for the measure of angle B. The same formula from the law of sines is, okay, sine of B over B is equal to sine of A over A. The only thing I don't know is B. So this is sine of B over, okay, B is 18. That's equal to sine of 56 all over 16. Again, I'll multiply 18 to the other side of my equation. Sine of B is equal to 18 times sine of 56 all divided by 16. This is really similar to the previous problem. If I type this into my calculator, I'm going to get the exact same thing as last time, right? Yeah, I get 0.9326672691. So if you want B, you have to take sine inverse of both sides of your equation. It leaves you with B, but if I type this in here, it tells me 60, if we round again, it's 68.9, but that can't be right. Look at this angle. This angle is more than 90 degrees. So this is wrong. There's an easy fix for this. When we define the sine inverse function, it always gives you an angle between negative 90 degrees and positive 90 degrees. So this is a problem. It doesn't give you the angle that you need. But there's a very easy way to get it. The 68.9 value that the calculator gave you back, that's actually this angle here. So when your angle is greater than 90 degrees and you use sine inverse, it's not giving you the angle you want, but it's giving you this other angle over here. It means it's very easy to solve for the correct angle because the sum of these two angles is 180 degrees. So for this problem, you just have to watch out for this. From my picture, I knew this was wrong. It should have been greater than 90. It wasn't. Therefore, if you want to solve for the correct one, you take 180 degrees and you subtract off 68.9 degrees to give us the correct value of 111.1 degrees. So this is the value that you want to use for the other triangle. And the reason for that is this process will only give you something that's less than 90. And in the picture, you want something that's greater than 90. So you can subtract from 180 to get it. That being said, the rest of this process is very similar to what we just did. The sum of the three angles is equal to 180 degrees. So if you want to solve for C, you can take 180 degrees, you can subtract off 56, but this time you're subtracting off 111.1 degrees. That means C, it's a small angle, it's 12.9 degrees, but that makes a lot more sense in the picture. I was anticipating a very small angle. And the only thing we don't know is the length of side C, but we can use the same exact law of sines to solve for it. C over sine of C is equal to, let's say, A over sine of A. The only thing I don't know is lowercase c, but c over sine of 12.9 is equal to 16 over sine of 56. I'll multiply this to the other side of my equation. That is, c is equal to 16 times sine of 12.9, all divided by sine of 56. I'm just going to type that into my calculator. 12.9 divided by sine of 56. Okay, I got c is 4.3. Yeah, these values are different, which is good. I mean, it's a completely different triangle. The values you get should match up what you see in your picture. And the idea is this. When you go through this process and use sine inverse, if the angle is less than 90, but from your picture, you know it's got to be greater than 90, you want to subtract it from 180 degrees.